Hey y'all, today we're going to prove one of the most beautiful equations of all of mathematics. It is Euler's identity. It is, in my opinion, the most elegant equation in mathematics. It ties together all the major elements of math into a nice, simple formula. Well, let's get started. Also, before we get started, if you are not familiar with Maclaurin Series or Taylor polynomials, you may want to check out my video over Maclaurin Series and Taylor polynomials so you can kind of understand what's going on. But that's the method I'm going to use in order to prove Euler's identity, or derive it, as we say. So first off, we have to use a little bit of imaginary numbers. Hope you'll remember I to the first power, it's just I. Also remember that I is really just the square root of -1. So when we do I squared, that's going to end up being -1. I cubed, negative I to the fourth is just going to be 1, because we're just basically taking, I squared times I squared. And then I to the fifth is going to end up being just I again, and then we're going to be back to -1. And so this thing is all cyclical. And so we end up with this. All right, so one thing, if you don't know Maclaurin series, here's one of the basic Maclaurin series that you end up having to know, is just this Maclaurin series for e to the x. And so what we realize, when you've studied Maclaurin series, that e to the x is equal to this infinite sum right here that I'm showing you. And so what we're going to do, though, is we're going to substitute, just like we would substitute into an equation for f of x, we're going to substitute ix in for x, right? So we're going to replace all the x's with ix, just like you would do if you were going to plug in a number into f of x. You would just plug that number in, right? And so we're going to do that. So ix, when we do that, we're going to get 1 plus ix plus ix, and that's going to be squared over 2 factorial plus ix to the third over 3 factorial. We can keep going on and on with this. And I think about 5 terms will probably do it. Well, maybe we'll do one more. We'll do up to x to the 6th degree. Maybe it'll show it a little better. But this goes on and on forever, okay? Now, this doesn't mean a whole lot like this, but the reason why we did all those values at the beginning is so that we could simplify this. So we could realize that this is just going to be 1 plus ix. And when we have I squared, that's going to be -1. So we'll say negative ix squared over 2 factorial. And then we have minus ix cubed over 3 factorial. Plus, and then we have just back to the beginning, right? So x to the fourth over 4 factorial. Plus ix to the fifth over 5 factorial. And then we've got this back to negative x to the 6th over 6 factorial, okay? And so that's basically, and this would continue on and on and on. Now, the next thing we want to do is we want to construct a Maclaurin series for cosine of x plus I sine of x. So again, if you're not familiar with Maclaurin series, you can check out the video. I will derive these Maclaurin series for you. But basically, if you've taken a BC calculus class, you should know both of those Maclaurin series and where they come from. This idea is, again, we could plug in any number into this series and it would generate the same values as sine, and they are equal to each other. This series does equal cosine as the number of terms goes to infinity, this infinite series. And the same thing with sine. Now, we're going to come up with cosine of x plus I sine of x. We already have the value for cosine of x. We just need to come up with the values for I sine of x. And that's just going to involve us multiplying both sides of this equation by I. So really distributing I to every term of this equation. And so we're going to end up with this I sine of x equals ix minus ix cubed over 3 factorial plus ix to the fifth over 5 factorial. And this would just keep going on and on and on and on forever. Now, we're going to go ahead and we're going to put these together. So if I go ahead and put these two together, we have this cosine of x plus I sine of x. We're just going to combine like terms between these two series. Well, they don't have any like terms, so it's really just aggregating these terms, right? So 1 comes from the cosine plus ix from the I sign, and then minus the x squared over 2 factorial from the cosine, and then minus x cubed over 3 factorial from the I sign, plus x to the 4th over 4 factorial from cosine, and then again from the I sign, we have the I x to the 5th over 5 factorial, and then minus x to the 6th over 6 factorial, which came from, again, the cosine. And so what I want y'all to notice here is if we look at these two series, the Maclaurin series for e to the ix and the Maclaurin series for cosine x plus I sine of x, they are exactly the same, right? I mean, take a look at that. They are exactly the same, which tells us then that e to the ix will then be equal. If each of these is equal to the exact same series, then they themselves must be equal to each other. So e to the ix is equal to cosine of x plus I sine of x. And so now that we have this relationship, we can just plug in, for x, we can plug in pi. And so this e to the I pi is going to equal cosine of pi plus I sine of pi. And hopefully you remember from your unit circle that sine of pi is 0 and cosine of pi is just going to equal then -1. So all of this equals -1. And so it leads to this conclusion that e to the I pi equals -1. And this is beautiful on for many reasons. And this is not even Euler's identity. I'll get to Euler's identity in a second. But this is beautiful for many reasons. And one thing is we take Euler's number, which is, is an irrational number, that goes on and on forever. We're taking an irrational number raised to an imaginary irrational value of pi, and yet the answer comes out to a nice integer value. We've also never seen Euler's number and pi in the same room together. It seems like pi is, in geometry, it's this, the circumference divided by the diameter of a circle. And we see it all sorts of geometric places. And then e, we see that in like a lot of exponential growth, exponential functions, also the derivative. We have e because it makes the derivatives of exponential functions base e really nice and easy to work with. The same as the natural log is super nice derivatives to work with. And so we really don't use these too often and think that most students don't even see that there is some sort of relationship between them. Clearly, since we provide this relationship that whenever you take e to the I pi, it is equaling -1. So behind the scenes of these math constants, they are linked in some sort of way. And so that's kind of one of the more beautiful things that I think people see. Now, Euler's identity is actually e to the I pi plus 1 equals 0. And the reason why we do this is this kind of involves all the major elements in their forms, where you have e pi, the imaginary unit, the real unit, and then equaling 0. Hope you found this video interesting. It is one of the most fascinating conclusions of math. Hope you enjoyed it. Thanks.